All right, over the next 2 days, we are going to talk about periodic trends. There are 4 periodic trends, and these are pretty much just pieces of information that you can get from the periodic table based on where that element is located. Yesterday, you went to the computer lab and you started to color code some of the values or the numbers for these periodic trends. And hopefully with that color coding, you started to see a pattern emerge, usually from left to right on the periodic table. You can see the colors start to change as you do that activity. So we're going to talk about 2 of the 4 periodic trends today, explain what they are. Hopefully you'll get a pretty decent understanding of them, and then we'll do 2 more tomorrow. The one that we're starting with is probably the easiest one to understand what it is, and that is atomic radius. When you talk about radius in geometry, what is it? What shape are you talking about? Circles, and radius is from the center to the edge. So basically halfway across the circle. We talk about atomic radius. We have to put 2 atoms side by side, which pretty much are circles. And then we measure the distance between their nuclei. Take that distance and divide it by 2, and that gives you the atomic radius. So atomic radius is the same as the radius of a regular circle. We have to measure it a little bit differently, because if you're thinking about trying to use a microscope, like an electron scanning microscope, to measure the size of an atom, it's pretty easy to find the nucleus with that sort of equipment. The nucleus is very dense. It's a little bit larger in terms of what you're looking for. When you're trying to look for the edge of the atom, though, you're in the electron cloud. And it's really difficult, nearly impossible, to figure out where the edge of the atom is. So what they do instead is put 2 atoms side by side, just like they would be in like the solid form of that element. Look for 2 nuclei that are next to each other, figure out what that distance is, and then cut it in half. And that's how we figure out what atomic radius is for each individual element. Here's how this trend works. As you move down a column from top to bottom, atomic radius increases. The size of the atoms go up as you move down the column. This is another way of saying that as you move down the column, the atomic size increases. If the radius is larger, the size of the atom is larger. So if I gave you 2 choices, which one is larger, oxygen or sulfur? Sulfur. How about carbon or germanium? Germanium. Seems pretty simple so far. But the other trends that we talk about, at least 2 of the other 3, the explanations of those other trends come back to this one idea. So it's important that we get this one idea first. Size increases as you move down the column. Why does that occur? This part of the explanation is pretty easy to understand. What energy level does carbon end with? What's its electron configuration end with? Is it a 1 or a 2? 2. What energy level does phosphorus end with? 3. You should know from our electron chapter that every time you go down a row, you add an energy level. Carbon would end with 2, phosphorus would end with 3, arsenic would end with 4. Every time you go down a row, you add an energy level. And if you're adding energy levels, what happens to the size of your atom? It's bigger. Outside electrons are in larger orbitals and higher principal energy levels. And overall, that makes your size bigger. We can also talk about how this trend works from left to right as you go across a period or across a row. As you move from left to right across the period, atomic radius decreases. The Y for this one is a little bit harder to understand. So I'm going to go to the board over here and we're going to play with some magnets and a marker. Let's start with hydrogen. How many protons does hydrogen have in its nucleus? 1. Should be a pretty easy question. So here's a proton. And then the first energy level would be, first part of our electron configuration would be 1s. If this is hydrogen, how many electrons do I put here? 1. Okay, now let's move on. Pretend it's helium. What do I have to add to make it helium? Another electron, which would make 1s2. What do I have to add in the nucleus? Another proton. We also technically should be adding neutrons, but for the sake of me not running out of magnets, we're going to ignore the neutrons for today. So just pretend that the neutrons are there, even though we're not putting them up. Okay, so we did hydrogen, we did helium. Lithium is next. What do I have to add for lithium? Another proton. And then where does its last electron go? 2s. Okay, what comes after lithium? Should be beryllium. What do I add for beryllium? Another proton. And an electron. Where does it go? In the 2s. Okay, let's jump across to boron. What do we add for boron? Same thing we had before. Add proton. Add an electron. What is this level now? What is this? 2p. Okay, here's where we're going to start with the explanation. If I were to move from boron to carbon, I would add, of course, another proton. I would also add another electron. The next electron that I add, this one right here, went into the same level as the one before it. And I also added another proton. We know that all these protons have what charge? Positive. All these electrons have what charge? Negative. What do positives and negatives do? They balance out, but if you're think about magnets, plus and a minus, they attract. We know that opposites attract. Okay, so positives and negatives attract. I'm going to take these electrons out of here just so you can see this a little bit more clearly. Pretend they're still there, we're just getting them out of the way. Every time I add a proton, the pull on the of the nucleus gets stronger. Every time I add a plus here, we get a stronger positive charge in the middle. When you add an electron that's in the same energy level, each electron in that energy level feels the pull of the nucleus as if it was the only electron in that level. each electron feels the nucleus pull on it all by itself. So if the nucleus gets stronger with every proton that you add, and the electrons that we add aren't getting any further away, every time you add a proton, those electrons in that shell or in that ring feel a stronger pull from the center. And if the pull from the center is stronger, what happens to the size of this atom? It shrinks a little bit. Those electrons get pulled in closer because the protons in the nucleus are getting stronger. Each electron in the shell feels that whole pull. Each electron feels the pull from the nucleus as if it was the only electron there. So as you add electrons in the same energy level, they get pulled in closer. The overall size of the atom goes down. Let's put that in words. The outer electrons are in the same principal energy level. That means every new electron that you add is the same distance from the nucleus as the one before it. Remember, we're talking about moving across the period from left to right. Every electron that you add is the same distance from the nucleus as the one before it. As you add electrons, you also add protons. Every time you add an electron, you also add a proton, stepping across the periodic table from left to right. As you add protons, the positive charge of the nucleus increases. The nucleus gets stronger. So the end result is that the electrons get pulled in a little bit closer. If the electrons get pulled in closer, then the size of the atom shrinks. Okay, side note for atomic radius. Earlier this week, we talked about how you make ions. You make ions when an electron is lost or gained. We can also compare the size of the ion to the size of the original atom. So if an electron is lost, then we make a cation. Cations are smaller than the original atom. The easy explanation for this is that if you pull off an electron, it would make sense that the atom is smaller. It's not quite the right explanation, but it works in terms of having an easy way to remember this. The true explanation has a lot more to do with the charge of the nucleus, like we just talked about. If you take one of those electrons away, the nucleus is that much stronger compared to all the rest of the electrons because you took one of the negatives off. So that allows it to pull those electrons in even closer. We can also talk about anions. Anions occur when you have added an electron. When you add an electron, the anion becomes larger in size than the original atom. And again, the easy explanation or the easy way to remember it, it makes sense. If you add something to an atom, that it would be larger than it was before. The more correct explanation would be if you're increasing the negative charges while not increasing the positive charges, that attraction between the two, then the electron side would be winning and they would be able to hold their distance. Okay, the next trend is ionization energy. And before we talk about ionization energy, we have something to see. So, the difference that you saw between those two reactions is because of a trend called ionization energy. ionization energy is the amount of energy that's required to remove an electron from an atom. In other words, it's the amount of energy that's required to make a cation. If you're taking an electron away, you are making a cation. You have to put energy in to get that electron to come off. Electrons and protons kind of work like magnets. They don't just fall apart by themselves. You have to put energy in to pull that electron away from the atom. What you end up with then is a free electron, because you pulled one off, and a positive ion, which we should know from earlier this week is called a cation.
What happens to the electron after that? Does it just hang out wherever you put it, or?
Usually that is a process that happens during a chemical reaction, and so that electron would go add on to something else most often. When you're talking about ionization energy, the amount of energy that it takes to remove an electron changes depending on how many electrons you are removing. The first electron is the easiest to remove. The first electron is the easiest to remove. Again, that has to do with the pull or the attraction between the nucleus and the electrons, because if you just take one electron away, you're not changing the strength of that attraction very much.
I think everybody's sick because everybody's coughing.
If the nucleus has the same number of protons and you start to remove more electrons, then you have a greater positive charge compared to a smaller negative charge. That attraction or that pull on the electrons is that much more unbalanced. Every electron that you take off gets harder to remove. So the first electron is the easiest to remove. That's the one that takes the least amount of energy to take off. The second, the third, the fourth, and so on take more energy every time. And that's what this little kind of math statement here says. The first ionization energy is less than the second, which is less than the third, which is less than the fourth. The first electron is the easiest to remove. After that, it takes more and more energy every time. I usually use the comparison of a student with a full pack of gum. First friend comes up and says, "Hey, can I have a piece of gum?" And you say, "Sure, here you go." Second friend, "Sure, why not?" Third friend, "Absolutely." Before you know it, you've got 15 friends that you didn't know you had. You get down to your last piece of gum, the next person comes up and says, "Can I have a piece of gum?" And you go, "Wait a minute, I only got one piece left for me." You hold on to that last piece a lot tighter than you do the first piece. Same is true for electrons. The first electron is the easiest to remove. There are a lot left. After that, it gets harder. Each additional electron that is pulled off takes more energy than the previous one because the electrons are pulled closer to the nucleus every time you take one off. The attraction between the nucleus and the electrons gets stronger every time because you have more of an unbalance. how does this trend work when you're talking about looking at the periodic table? Ionization energy decreases as you go down the column. As you move down the periodic table from top to bottom, it takes less energy to remove the first electron. As you move from left to right across a period, ionization energy increases. It gets harder to move electrons as you go from left to right. This is the opposite of atomic size. Atomic size increases as you go down and decreases as you go to the right. So when you're talking about atomic size, the largest atoms are found at the bottom left corner. The further away the electrons are from the nucleus, the easier it is to take them. The closer they are to the nucleus, the harder it is to take them. So the electrons that are going to be closest to the nucleus are going to be the ones that are the smallest, which would be at the top right. Ionization energy is opposite of atomic size. The larger atoms have a lower ionization energy. The smaller atoms have a higher ionization energy. Because ionization energy is related to size. It's easier to pull electrons off of a large atom because they're further away from the nucleus. This is why sodium reacted more than lithium, or reacted faster than lithium. Lithium is smaller. Its electrons are closer to the nucleus. It is harder to pull them off during a reaction. Sodium is larger. Its electrons are further away. That means it's easier to pull them off during a reaction. It has a lower ionization energy. So sodium reacts more quickly than lithium does. Ionization energy, when you're talking about metals, tends to correspond to reactivity. The lower the ionization energy, the more violently that atom will react, or more quickly it will react. So electrons that are far away from the nucleus are easy to take. That means there's a small ionization energy.